This is video 7 in our series Analytical Mechanics. The playlist for all the videos is featured at the website digital-university.org. Here we're continuing where we left off in video number 6, where we're considering the very simplest type of harmonic system possible, where we have a spring attached to it as a block of mass m, and we displace it a certain distance a, release it, and it goes back and forth along this x-axis, this frictionless x-axis. And in video 6, we were considering the system just from an energy standpoint, and at the end of the video we derived this equation where the velocity of the block at any position x is determined by this equation. Now we can probably use this equation to get more information about the system if we consider the velocity for our simple system as just dx dt. And now with just some simple manipulations, we can put this over on this side of the equation and put this over here. So we have it like this, dx divided by the square root of a squared minus x squared. That will equal the square root of k over m times dt. And if we can integrate both of these like this, that's a constant, so we'll leave that to the outside of the integral sign, but that then would give us an equation of x in terms of t, so that would mean then that we would know the position of the block at any particular time. Of course, that's a trivial integral, that's just going to be t plus some arbitrary constant. Now for this integral, we have, this is a constant minus a variable. Usually that's setting us up for a trig substitution. Remember, cosine squared plus the sine squared equals 1. Or we can say that 1 minus the sine squared that's the cosine squared of theta. So we want this, here we have a constant minus a variable. The constant here is 1. We want to see if we can make this, a constant minus a variable, look like this by using a trig substitution for our variable x. So let's try it saying let x equal a times the sine of theta. So dx, that will just be a times the cosine of theta d theta. So we know what that is going to be. Now down here for the square root, a squared minus x squared, but x is this. So you have a squared sine squared of theta. And we can factor out the a squared. That will leave us with 1 minus the sine squared of theta times a squared. We can take a squared to the outside of the square root sign, and that will look like this. And that's the cosine squared, but the square root of that is the cosine. So our original integral, when we put this substitution into it, that is going to be dx is this, a times the cosine of theta d theta, and the denominator is this, a times the cosine of theta. Of course, that's 1. And the integral of d theta is theta. And we'll have an arbitrary constant of integration that we'll deal with in a little bit. But now, what is theta? So we go back to our substitution. We see that the sine of theta equals x divided by a. Now, if I take the inverse sine of each side of this equation, the inverse sine of the sine, that's just theta. And that's going to be the inverse sine of x over a. So theta equals the inverse sine of x over a. So this integral equals this. So we have now the inverse sine of x over a. That has to equal this. Of course, that's just going to be t when we integrate that time. So that will equal the square root of k over m times t. And then from each integral, we have an arbitrary constant of integration from this one and from this one. So let's just combine those together. So here's what we have so far. We can take the sine of each side of this side of the equation, and take the sine of that side of the equation. Of course, the sine of the inverse sine, that's just going to give us x over a. So we have x divided by a will equal the sine of this quantity. Square root of k over m times t plus our constant. And now we can multiply both sides by a. And here we have this equation. So here, of course, a is the amplitude. That's how much we stretched or compressed the spring by. And if we know that, then at any time t, we know the position of the block along the x-axis. And we can take the derivative of this, and that would be the velocity of the block. And that would equal, that's dx dt, and taking the derivative of this side with respect to t, this is going to come out, so that will equal the square root of k over m times a, and the derivative of the cosine, or the derivative of the sine, is plus the cosine, so this would be the cosine of square root of k over m times t plus the constant. So this expression right here gives us the velocity of the block at any time t. This expression gives us the position of the block at any time t. And remember, these were derived from this equation, the velocity of the block at any given position. Then once we knew that information, we could use that to determine the position of the block at any time, and then the velocity of the block at any time. Now what we want to do is consider the period of this system. Before we do that, let's go back to here. To solve this integral, we use this substitution. We did not have to do it that way. We could have used the cosine of theta here instead. And if we did that, then x would come out to equal a cosine function instead of a sine function. And either one of these is a valid answer. We're going to work with this expression though. So let's go up to here and make some room. And the equation that we derived for the position of the block along the x-axis at any time t was x equals a times the sine of, and that was the square root of k over m multiplied by the time, and then we also have this constant here. And we'll discuss later on the meaning or the significance of this. We want to ask first this question. If we, say, displace the block out to here and release it and let it go, so it's going to go from here over to minus a, then back to its starting position, how long does it take to do that? And that length of time, which we'll designate with tau, that will be the period of the system. And of course, by the nature of the period, that means that when it undergoes an oscillation of one period or a cycle of one period, the block ends up wherever it started at. It was here, then it ran for exactly one period of time, so from here back to where it started from. Well, here's the equation that governs the motion of the block. It's either a sine or it could be a cosine function, either one. But the period of either one, the sine or the cosine, it has a period of 2 pi. So we know that this has got to have a period, this has got to come out to be a value of 2 pi when we're dealing with the period of the system, tau. So let's think of it like this. We can say, we'll work just with what's inside of the sine function here, this quantity. Let's say we have it like this, the square root of k over m multiplied by a certain time plus c minus square root of k over m multiplied by a different time plus c, that has to equal 2 pi. But it's going to be periodic. Well, these cancel, and we have the square root of k over m times t2 minus t1 equals 2 pi. But this time elapse, by definition, that's the period tau. So let's write that in here. So we have this square root, k over m, times tau equals 2 pi. Or we have the period that equals 2 pi. And then we're going to have the square root of m over k. So here then is the period of our system. Notice that it does not depend on the amplitude. So whether we pull the block out, say at distance a, and let it go back and forth like this, or will we pull it all the way out to here and let it go back a further distance? The amount of time it takes to do it for either case is the same. It's completely independent of the amplitude. It depends only on the mass of the block and the spring constant. Now, let's talk about this a little bit more, the period, tau. We say that, by definition, it's the time that's required to complete one cycle. So if we take the reciprocal of this, that would be the number of cycles per time. For example, suppose we say we have a system where tau equals 1/10 of a second. So that means it would take 1/10 of a second for the block to go from here over to here and back to its starting position. Well, then, if it takes 1/10 of a second to do that, obviously in 1 second, it's going to go back and forth 10 times. So the reciprocal of the period is 10 cycles per second, or that's the frequency. Now, in many books, they don't talk about cycles per second. Instead, they refer to 10 hertzes, where 1 hertz is 1 cycle per second. But what we're interested in then is the frequency is the reciprocal of the period. So if this is what the period is, then the frequency is the reciprocal of that. So F equals, and that's going to be 1 over 2 pi times the square root of k over m. So that's the frequency of the block going back and forth, how many cycles there are per second, or whatever our unit of time is, right here. Now, we can gain some more insight of our system if we consider it like this. Here's the block, displace a distance a, pull it out, release it, and let it slide back and forth. Well, this back and forth motion we can simulate with a circular motion. Let's say when the block is over here at its displacement plus a, we designate it with this arrow on the circle. And then when it moves to here, to where the spring is no longer stretched or compressed, then we can designate it like this. And then when it goes to here over at minus a, we can designate it like this. And then when it goes back to the equilibrium position, where the spring is neither stretched nor compressed, designate that like this. And it goes back to here, then this goes over to here. So the back and forth motion like this can be represented as an arrow going around the circle like this. And clearly, the more rapid it goes back and forth, then the more rapid this arrow goes around our circle of reference. But we can be more analytical about this. We say that the frequency, that's the number of cycles per time. So if we have frequency times time, that's just going to be the number of cycles. Now for circular motion, 1 cycle, that's 360 degrees, or 2 pi radians. So if I multiply the number of cycles times 2 pi, that's the total number of radians. Or if I multiply that by 2 pi, that's the total number of radians. So 2 pi times the frequency multiplied by the time is the number of radians. Now the frequency, that's the frequency of the particle going, or the block going back and forth along the line. The number of radians, that would be the number of radians completed by the circle, by the arrow going around the circle. We'll divide both sides by t. So we have 2 pi f equals the number of radians divided by time. That's angular frequency. So we have 2 pi times f equals the angular frequency. So this is going back and forth with a certain frequency, f. The arrow is going around the circle with an angular frequency, omega, And if we know this frequency, multiply it by 2 pi, and we'll have this frequency. Now let's see how we can use that information. We want to go to here. This is what the frequency is for the block going back and forth, 2 pi f. That's just this, the square root of k over m. And that's supposed to equal the angular frequency. So here's our system going back and forth. If we want to represent it as an arrow going around this circle of reference, then the angular frequency of that arrow going around the circle is the square root of k over m. So that means then right up in here we can replace this with omega. So let's do that, and once we do that, that will take us very close to the end of our video. That is now omega times t. And this should make sense, because this is angular frequency, the number of radians per unit of time, multiplied by the time. That's going to be radians. So this gives us an angle that we're taking the sine of. Now, what does this mean? That tells us the position of the block at time t equals 0, depending upon how we set up the initial conditions. For example, let's say that here's the spring with the attached block, and then we displace it by a distance a. Well, let's say then that it's sitting right here. We call this time t equals 0. Then we start pulling it back. So by the time the block gets over here to position A, that's going to be at some time greater than 0. So the way that we set up the initial conditions, we're saying when t equals 0, then x equals 0, because there is no displacement here. The spring is neither compressed nor extended. So that means then 0 equals a times the sine of that 0 of c, then clearly c has to be 0 with these initial conditions. Let's get this in better focus. There's our equation for x, the position of the block. When t equals 0, x equals 0, because it's sitting right here where the spring is neither compressed nor extended. So we have 0 equals a, that's 0, times c. So with this type of initial conditions, c is going to be 0. Now, let's consider the same situation, only let's say it's like this. We pull the block back, and then once it's displaced by that distance a, we call that time t equals 0. And then we release it. So now we're saying when x equals 0, when t equals 0, x is a. So now we have here a equals a times the sine. T is 0, so that's 0 times the sine of c. So under these initial conditions, c will equal pi over 2. So we can think of this as like a phase angle, and it depends upon the initial conditions of the problem. And what we're going to do in the next video is actually continue our discussion of this extremely simple system. In video 6, we begin our discussion considering the energy aspects of this. In the next video, we'll look at this from Newton's equations, and that will give us a second order differential equation to solve. We'll do that and then compare the results of that with this result. And also in the next video, we'll talk about this phase angle some more. So come back and join us for that video. Then once that is finished, we'll have the background where we can consider more complicated systems.